I solve every problem with infinite precision. This is 2740. Find the value of the partition. Okay, so this problem is sourced from the most recent competitive programming challenge competition, and it's classified as a medium, but certainly, like most problems, the classification system is either inaccurate or not all-encompassing, but I'm not going to elaborate further down that rabbit hole because I have in previous videos, and then it just turns into a rambling mess. But that's just to say that this problem is a medium, but it's more so an easy, but also I understand why it could be classified as a medium, so it's somewhere in the ether in between two realities of being classified as an easy and classified as a medium. So it's an easy medium. I don't know how else to articulate that point. Okay, so you are given a positive integer array nums. Okay, so you just have this array nums. All the elements are positive. All right. Partition nums into two arrays, nums1 and nums2. Okay, so I take this initial array, nums, right? I have nums, and I'm going to partition it into nums1 and nums2. Okay. Now, what are the rules of the partition? Well, each element of array nums belongs to either the array nums1 or the array nums2. Okay, so you have to take all the elements and you need to use all of them, right? From the source nums, you have to use every element in the source nums, and you take that number and what? Both arrays are not empty. Okay, so you have to have at least one element in each array, and the value of the partition is minimized. Oh, what? Okay, so then the value of the partition is max of nums1 minus min of nums2. So if I'm taking nums, I don't have to like split at a certain point. If I have, for example, nums equals 1, 2, 3, 4, I could, in theory, have nums1 and nums2 as such, right? I could put 1 over here, then I could put 2 over here, I could put 3 over here, and I could put 4 over here. Meaning there doesn't have to be like some sort of continuation, right? It doesn't have to be continuous. I could, split it however I want. I just have to use all elements. And likewise, I could put 3 over here. I could put 3 over here and leave this one alone. Right, so I have a lot of freedom in terms of what I do. I just have to ensure that there's an element in each array, at least one element. And, I'm using all the elements from the source. I can't, neglect any single element. Okay. And now we want to minimize the value of the partition. And the value of the partition is, so I'm going to call that, I guess, the value of a partition. Partition meaning a split into, this left element and this right element is defined here. It's the absolute value of the max of one partition, we'll call that nums1, minus the min of the other partition, nums2. Okay, so what we want to do is we want to take this original nums and we want to partition it into two separate nums1 and nums2 such that the max of num1 minus the min of nums2 is minimized. Okay, here max of nums1 denotes the maximum element of the array nums1, and min num2 denotes the minimum, right? So that's the max element. So the max of this one would be 4, the min of this one would be 1, right? So then you would have 4 minus 1, which is 3, so that would be the value of using this partition. Okay, so all right, we have 1, 3, 2, 4. I didn't even know that was the example, but okay. So we have example nums equals 1, 3, 2, 4. We can partition the array nums into nums1 equals 1, 2. So you move 1 and 2 over here, right, in this example. And then you have 3, 4 over here. And then the max of nums1 is 2. And the min of nums2 is 3. So 2 minus 3, negative 1. Absolute value is 1. And then you could exhaust all examples and get the answer. So, and then here, if you partition this with 1 in one side and then 10 and 100 in the other. The max of 1 is 1 minus the min of 10 and 100 is 10. 1 minus 10, negative 9, absolute value 9. And that just walks through that here as well. Okay, so 10 to the 5. So we're going to need either a linear or a log n solution in order for this to pass, right? N squared would give us 10 to the 10, so that's going to be much too large. So it's good to look at these constraints and kind of think about, what's the higher bound on something that would be acceptable given these time constraints, right? So, well, how did I come to this answer? How did I come to the answer to this problem? It's pretty intuitive, I guess, because what I want to do is I want to minimize the difference between the max of nums1 and the min of nums2, right? So I guess a similar problem you could think about first that would lead you to this solution is, well, how would I find kind of the best candidates to be the max of nums1 and the mins of nums2, right? Because I want to find the two numbers together, right? I want to find the two numbers together, right? I want to find a pair of numbers, A equals the max of nums1 and B equals the min of nums2, such that we have the minimum A minus B, right? So these will be just two numbers within our array, right? And how do you find the minimum difference between numbers? Well, if we look at an array like 2, 1, 3, 4, for example, right? If I grouped a number with 1, okay, I want to find, if I say A equals 1, right? Or let's say B equals 1. Or no, let's say A equals, I always do that. Let's say A equals 1. If A equals 1, what would be the number closest to 1 to minimize the difference, right? If I chose this to be 1 here, what number needs to be here in order to minimize the difference? Well, I could put 2 there, 3 there, or 4 there, right? The answer, of course, is 2, right? The number that minimizes the difference between two numbers is the closest number to that number, right? Like if I have numbers on a number line like 1, 3, 2, 4, 5, 6, what number is going to minimize 1? The difference of 1. That's the number that's closest to it, 2. Right? The minimum difference from a number is the number that's closest to it. Right? So it's pretty self-explanatory, right? It's like a self-recursive definition. The number that's going to minimize the difference for any number is the number that's closest to it. Right? So when I say, for 4, well, what number is going to be what number is going to minimize the difference for 4? Well, that's the numbers that are closest to it, right? 3 and 5. Okay, so in this problem, what I want to do is I want to choose A and B such that the max of nums1 and the min of nums2 are the numbers that are as close as possible to one another within the array, right? So if I take an example like, let's say, for example, something a little bit more complicated just to prove this point. Let's say our nums was 50, 52, 1, and 100, okay? So what I want to do is I want to figure out what is the pair. What is the pair of A and B such that A is the max of nums1 and B is the min of nums2 such that I have the minimum difference, right? So I could compare all these numbers to each other, but I just want to compare the numbers that are closest to me, right? So maybe what I want to do is if I only want to look at numbers that are next to each other, I should sort this system first. And that'll give me nums equals 1, 50, 52, 100, right? And then what I can do is I can say, well, what if I have A equal this and B equals this? Then the difference is 49, right? So if I do that, I get 49. If I move this over, I get the difference is 2. And if I move it over again, I get the difference is, quick math, 48. So obviously the best solution here would be to choose these two numbers, right? So the idea is if you want to find the minimum difference between two numbers, sort the numbers in the system and then go through and compare each adjacent pair, because those are the numbers that are as close to each other for each number, and then find out what the difference is between them. So what we need to do then is say, okay, for adjacent elements, this is as close as they can get. So can we somehow always devise a way where the max of one set is this number and the min of the other set is this number? Okay. And I think it's pretty intuitive how that would work always, right? If you have a sorted system, okay, so let's say we already have a sorted system that looks like such. Let's say we had a sorted system of A, B, C, D, E, F, G, H, I, J, K, da, 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 whatever, okay? Let's say we're looking at any two, or we'll do this even more generic, okay? Let's say we just had elements, then we had X, Y, and other elements. Can we make it the case such that the max of all of this is X and the min of all of this is Y? Well, if we want to do that, what can we do? Well, we can just say, let's make this one set and this the other. Remember that this system is already sorted, right? So we'll say sorted. So then you have all these elements on the left and all these elements on the right. Remember, since it's a partition, we can place things however we want. So the fact that we sorted it doesn't change anything. We just put everything that's smaller, including X on the left, and everything bigger than X on the right. So then we have nums1 equals everything up to X, and nums2 equaling Y and everything greater. So then the max of num1, because remember this is sorted, the max of nums1 equals X, and the min of nums2 equals Y, right? And this works in any position. Even if this was the last element, right? For example, if this was the last element, then this would just be empty, and then the max would be Y itself. So what I'm saying is, what I'm trying to allude to here is that no matter what, right? No matter what, you can always construct any two numbers for one of them to be the max and the other one to be the min, right? There's always a way, given these partition constraints, where we can construct a system where, you know, one element in the original nums is the max of some partition of nums1, and the other element is the min of some other partition in nums2. And that idea really is just to sort the system and then put everything that's less than the max number in the nums1 and everything that's greater than the min number in nums2. So then you always have this case where if you have it sorted, you can construct any XY. So what that basically means is we can look at any pair of numbers, and if the minimum difference is there, there can be a created partition where those two numbers are the min and the max, so then you just return the min. So this problem really just boils down to, right, like if you look at its fundamental components, it's equivalent to just kind of saying, you know what, this doesn't even matter. Like this case doesn't really, this information is kind of irrelevant because it can be constructed always. It can always be constructed where any two elements are the min and max. What we're really trying to do is just find A and B that minimizes the absolute value of A minus B, right? And I proved that here using the sorted idea, right? We're just trying to find two elements in our array that minimizes A minus B. That's all this problem is when you break it down into its kind of fundamental components. So in order to do that, we can just sort the system and then just go through pair by pair and try to find the minimum difference, okay? So let's go ahead and do that. So what we're gonna do is we're gonna sort nums. Now that's gonna take constant time. And now I'm gonna do something here that takes linear time, but just for the sake of simplicity, we'll do it the other way. Okay, so we'll say m equals float infinity. We'll call that res for the solution. And then we'll go for I in range 0 all the way to the length of nums minus 1. So we can look at each pair. And then we'll say res equals the minimum of whatever we thought the minimum was before. And then nums of I plus 1 minus nums of I. Right, because that's the difference between you and the adjacent element. And we don't have to do absolute value since it's sorted. So it's the next element. And then at the end, you just return res. And then I guess we can make this a 3-line solution if we do it like so. Okay. Local variable, equal sign. Very simple coding that I don't understand apparently. All right. Okay. So before I go into the runtime and space runtime and space complexity, let's just kind of quickly review what we did. So, you know, we took this problem and we thought about, you know, why did I do that? We thought about what is possible, right? What it really means to partition, how you can partition however you want. We looked at this like idea of the max and the min, and then we did that via an example. And then we looked at kind of, well, what is equivalent here? If we want to find for any pair of numbers, trying to summarize, and I'm only making it more complicated. The idea here is we look at what it means to find, you know, this minimum value. And we say, well, how do you find the minimum value just in an array, right, between two elements? Well, what you do is you'd sort it because for any element, the value that would minimize the difference is the element that's closest to it. So sort the system so then every adjacent element are the closest elements to each adjacent element, right? And then we prove that, well, for any max min pair in the system that's sorted, we can always devise a way where our element A is the max and our element B is the min. So then this value thing doesn't really matter. Instead, all that matters is just finding an A and B that minimizes this difference. And that's just as easy as sorting and then going through. Okay, so that said, let's say n is the length of nums. For time, well, we have to sort this system, right? So it's going to take n log n time. And then we have to look at all n numbers to find these deltas. All n minus 1 or big O of n. So that's big O of n log n plus n. So that's going to be shadowed by n log n. So that's n log n time. Okay. And then for space, well, I'm not sure if Python sorts in constant space, but there are like heap sort, right? There's in-place heap sort. So there's mechanisms in which you can sort in constant time. I mean, in constant space, constant time, that'd be great. You can sort in constant space, so you don't use any additional space. So this is O of 1. And then the way that we did this is also O of 1 space, right? Because I'm just updating one variable res for each adjacent pair. So that's constant space, total, constant space. All right, guys, everybody have a beautiful rest of your day. Peace out.